Okay, again, welcome to the next in our iGuide virtual consulting office sessions. Today, we're very excited to have Nemin Wu and Qian Cao share their information about the TorchSpatial program that they work with. We first heard about this last year with our Spatial AI challenge, and I'll let them introduce themselves more and start with their presentation. Remember to keep your own microphones muted during this presentation, and we'll have time for Q&A at the end.
Cool. Thank you, Diana. I'm Nemin, currently a PhD candidate at University of Georgia, major in geography and also like artificial intelligence. So Qian and I are gonna present one of our works in TorchSpatial. Qian, do you want to like give a quick introduction?
Yeah, sure. Hi everyone, I'm Jen, PhD student in the Department of Geography, University of Georgia. For this session, we will going to let Namin introduce the overall framework, and I'll go to introduce the benchmark metrics, and next I'll go Namin will go back to introduce the tutorial. That is our plan for this session.
Cool. Sounds good. So our work is like basically TorchSpatial is a location encoding framework for spatial representation learning. And so this research focused on the problem of spatial representation learning. And before I introduce SRL, I want to mention that traditionally, due to the lack of representation learning techniques for various types of spatial data, many pioneering research resorted to some compromised approaches to encode or decode spatial data. And one way is to perform feature engineering. For example, we've seen works extracting features from building polygons for building pattern classification. That's one way. And another way is to convert the spatial data, those vector data, to formats that's easier to be processed by the neural nets. For example, rasterizing some building polygons to images, and we can continue working on building the pattern generation. Because like for raster data, it's easier for us to use some encoders like CN or VIT to have some well-established NN models. However, like the previous approaches heavily relies on some domain knowledge, and it's usually harder to generalize to new region and tasks. So the SRL, spatial representation learning, is a set of techniques that can help us learn the spatial representations from various types of spatial data in their native formats, and at the same time avoid those manual feature engineering. And SRL is a fundamental problem in GeoAI and spatially explicit AI. The core research question is how to represent different types of spatial data like point, polyline, polygon, or raster into embedding space so that they can be easily utilized by deep learning models like the neural nets. But it's rather different to develop representation learning model for vector data because they usually have irregular structure. So we call those representation learning models correspondingly as the location encoder, polyline encoder, and polygon encoders. Our work towards spatial mainly focus on point, namely the location encoder at this time. But this is one of the most fundamental data types of spatial data. Here's like a quick example of like how the location encoder or like the location information can be used in some real-world task. For example, if you're given some images and your task is to classify or to tell what species is in those given image, sometimes it will be very difficult to distinguish them morphologically, especially if you look at the American white pelican and the great white pelican. They look very similar. They share the identical plumage, and they have similar beaks. So if you're not an ornithologist, it will be very hard for you to do the task to give the correct species name, and it's just very hard for computer or vision model as well. However, if you have some prior knowledge of the location information, for example, there's no American white pelican in your Asian continent, and there's no great white pelican in the North America. And then given the metadata of the image, like where the image was taken, then we can improve the model performance. That's how like we can why like location matters in some cases. And actually, spatial representation learning has facilitated the GeoAI development to solve a lot of different kinds of geospatial tasks in a supervised learning manner, including the spatial distribution modeling I mentioned before, and also satellite image classification, geographic question answering in geospatial semantics domain, and a well-indexed prediction in demography and sustainability research domain, and also weather forecasting, POI type prediction, and so on. However, currently there's no widely adopted framework to standardize the development of the SRL models. Also, we lack a standardized benchmark to systematically evaluate how spatial encoders impact the model performance. And lastly, there's a gap in our understanding of how geo-aware AI models may be influenced by those geo-biases. So given those kind of motivation, our TorchSpatial framework contains 3 key components correspondingly. The first one is a standardized location encoding framework that includes 15 recognized location encoder, and we use a unified framework that can help improve the scalability and reproducibility of the implements. And secondly, we have collected and pre-processed LocBench benchmark datasets. So we have cleaned 7 geo-aware image classification and 10 geo-aware image regression datasets that can be used for evaluating the location representation learning. And thirdly, we also provide a set of evaluation metrics to quantify the geo-aware model's overall performance, for example, accuracy for a classification task and RMC for regression task. And in addition to that, we also propose a new metric called Geo-Bias Score metric to evaluate the geographic bias as well. So here's the overall architecture of TorchSpatial. So from the left is the input of the geo-aware image datasets. So for each image, we have the coordinates along with the image in the metadata. And the input data are pre-processed and fed into the image classification or regression inference model framework. And then the model is tested on the benchmark datasets and then being evaluated by a set of evaluation metrics. The idea of location encoding can be understood as a feature decomposition process, which decomposes the, for example, coordinates, the 2-dimensional vector of longitude and latitude into a learning-friendly high-dimensional vector. As we mentioned, we used a unified and flexible framework to support the development of location encoders. So here, this equation shows the structure for that framework. The X is the input original coordinates, location coordinates, And a PE here is a position encoder, which is the most important component which distinguish different location encoder. Usually the PE, the position encoder, is a deterministic function which transform X to a W dimension vector, so-called the position embedding. And the purpose of position embedding is to do location feature normalization and composition so that the output position embedding is more learning friendly for neural nets. And NN is just a learnable neural network component that maps the input position embedding to the location embedding. So in our framework, we just adopt a very simple way, just like using MLP or dense layer for the NN part. And it's worth mentioning that during the inference stage, for classification framework, it consists of three components: the location encoder, image encoder, and inference component. Inspired by prior studies, the location information is incorporated as a Bayesian spatial prior here. And the model independently classifies the image and location data through a distinct image and location classifier, and then the final classification result is derived by performing element-wise multiplication on the output of the two classifiers. So this way it enables some pre-training of image encoder, and after the pre-training we freeze the image encoder so that it allows for isolation and evaluation of various location encoders' performance. Well, for the regression task, we use a more straightforward approach that the features or embeddings extracted from both the image and location data through their respective encoders are concatenated together and feed into a feed-forward neural nets to predict the continuous value. So we use the combined feature as the input. And later, then Tian's gonna talk more about like LocBench and our experiment setup. Oh, I think you're unmuted. You're muted.
Okay, now I guess you can hear me. So LocBench is the name of our benchmark. It means location bench. We have two categories of data sets in our benchmark. The first one is geo-aware image classification task. So it includes three tasks. The first one is fine-grained species recognition. Nemin already explained why fine-grained species recognition is geo-aware, because different species, they may have similar appearance in the images, but they actually have extremely different locations correspondingly. And for the second task is flicker image classification. Flicker image is image actually uploaded by Flickr users from all over the world. They have different 100 categories of objects labeled in this dataset. And for the next task is remote sensing image classification. We have functional map of the world containing 63 categories of land uses. And this is also a very typical geographic aware image classification task. For the second category of the LocBench, we offer regression data sets here. So the differences between the classification and regression, you must be very familiar with that. The regression means we predict the continuous target variable for the image. And for these categories, we have variables like landscape, urbanization, and United Nations Sustainable Development Goals indicators. For example, we have forest cover ratios, elevation, night lights, population density, etc. So this is the LocBench we offer. You could access these datasets through via the QR codes we will provide later. And apart from the benchmark, we also provide a set of geographic bias metrics. The first thing is, what is geographic bias? Well, when we look into the left figure, it shows us the spatial distribution of training dataset in INET 2018. So actually, in many worldwide datasets, you could see the similar pattern. Those images or datasets observations are densely distributed in North America and West Europe, but in some other like undeveloped countries like China or some other countries in Africa, and you could only see sparse observations. So that is a geographic bias we mean here. Also, apart from the geographic bias in datasets, you could also see model performance bias from the right figure. In some model may perform well in North America because of the data set is good, or maybe it is because it's more suitable for this area, but they may perform worse in tropical areas or North Pole, South Pole, some areas like that. So apart from data set, model performance also have geographic bias. The question is, how can we quantify those bias? That is why we propose this set of geographic bias score. Okay, so the first step is to extract a low performance observation, this sample point, and we extract the neighborhood by a radius r. And then we have two scores. The first one is unmarked SSI. SSI means spatial self-information, and we calculate this metric by setting all performance values to 1 and mixing with randomly distributed virtual background points. Like these little green crosses, they are randomly distributed with virtual background points. That unmarked XSI can reflect the intrinsic data bias in the dataset. And for the marked SSI, we compute the SSI by marking the high performance, the red dots as positive one. Oh no, actually it should be the low performance. Low performance should be the red dots, and the green dots are high performance. And we mix these observations with randomly distributed background points, just as the previous unmarked SSI. And this marked SSI can reflect the geographic bias in model performance. So we have two sets of two scores, one for bias in dataset and one for model performance. If you want to know more information about what is spatial self-information, you could access to the paper I listed here, probing the information theoretic rules of spatial dependence measures. And you could also refer to another paper we just released recently on archive Geo-Bias. And this paper explained more about the geographic bias score. And we also proposed some other geographic bias score in this paper. And we're going to do more work on this work, and we are going to propose a new package in the future. This is a geographic bias score. And what about the experiments results? This page shows us the image classification results. We use top 1 accuracy as the metric to tell you the performance of all the location encoders. So the first row, the A category, is a no prior model. It means it's an image only model, no location encoders in this row. And the category B means 2D encoders, 2D location encoders, and C is a 3D location encoder, D is GPT-4V. So in this table, we could see that no matter is 2D encoder or 3D encoder, basically all the location encoders can facilitate the performance based on the no prior model. And as for the GPT-4V, the performance is worse than the location encoders and the image model. And we could see the similar pattern in the image regression results table. We evaluate the results via R-square. So we could see that the location encoders have higher performance than the prior model. This is another table for image regression results, have a similar patterns. So one interesting thing is about geographic bias. In this table, we evaluate the geographic bias of the image classification, especially the top one accuracy. So in this table, we could see that even though previous table showed us the location encoders can facilitate the performance, the overall performance quantified by accuracy, but they also enhance the geographic bias. Basically, most of the location encoders can enhance the bias except one encoder, the tile encoder. And the tile encoder is the most widely used encoder. It splits the word into different tiles and then encode the tiles. Is a very like vanilla location encoder. So in our experiment, it shows that this encoder can balance the performance, the overall performance, and the geographic bias. As for the geographic bias for regression models, we could also see that the location encoders enhance those geographic bias based on the no prior model. But one interesting thing is that for these datasets, for the first cover or population density, these kinds of regression datasets, the geographic bias actually didn't increase a lot compared to the no prior. And we think it is because these datasets are actually special, different from the previous ones like functional maps of world, because these datasets are uniformly distributed across the world, not like the previous map I showed to you with a very unbalanced spatial distribution. And that might be the reason why we adding location encoders but didn't enhance the bias. So to conclude, for TorchSpatial, we offer 15 location encoders in our package, and we also have image classification datasets, have regression datasets in Figshell. We open source all those datasets, and you can access to our paper via this QR code, and also we have tutorials on our website and GitHub page. So yes, basically these are all the slides I want to show to you, and then I'll give the floor to Naomi, and she will show you the tutorial how to implement all those location encoders in your own work.
Oh, well, cool. So if you go to the main page of our GitHub repo, there's one tutorial here, which provides a quick walkthrough for our pipeline, starting from the environment settings, the dataset download, and if you just want to use a location encoder, you can just like use this section to initialize your own location encoder and integrate it into your own model framework. And if you want to like rerun our experiments on location bench, then we also provide some hyperparameters for you to play around and replicate the experiments on different set of data sets. And I think we also have like saved hyperparameters somewhere. I think it's evaluation batch file and run batch file that you can make use of. Yeah, so that's basically about the tutorial, and we also add the tutorial, the data sets and tutorial to the iGuide platform as data set and the model card. Yep, that's basically the tutorial. I want to mention that we used to have a like Python package published with the same name, TorchSpatial, but we've receiving some issues saying that some dependencies are not up to date, especially remember NumPy is very using a very old version, so we are currently maintaining that package. So I've yanked the package on PyPI, and I'm working on like updating the dependencies, and I will release it hopefully by the end of this month, so that you can also pip install the TorchSpatial package to initialize your own location encoder. Yeah, that's it. So any questions for us?
Yeah, people can, I know there is one question on chat, but people can also feel free to unmute themselves and ask questions.
Okay, for the question in the chat, in figure 1 of your paper, how did you decide the number of labels or categories for 3 tasks for GeoAI image classification? For example, BirdSnap use 500 categories, WebCC use 100 categories, remote sensing using 63 categories. This label sizes appears much smaller than the typical ImageNet classification size. Well, to answer this question, actually we use the categories provided by the dataset maintainers. So we didn't modify the categories or sample the categories. Like if YFCC is original have 100 categories, then we have 100 categories. That is the reason they may seem very diverse, and the label size appears smaller than the typical ImageNet classification size. Hope I answered your question.
Sorry, any other questions from people on the call?
Well, if there's no more question, I also want to mention that even though our package and our benchmark are designed for image classification and image regression tasks, actually you can also utilize location encoder in other tasks using GeoAI. For example, like text classification or text regression models, you can also add our location encoders, trying to concatenate or use some other methods to employ the location encoder in your own architecture.
That's wonderful. Hey, Carol, you have a question?
Yeah, so thank you for the presentation. Very detailed explanation of the results. So I'm wondering, so you have various encoders and you showed sort of one type of applications. And so I wonder how how transferable these results are. Let's say if I have a different types of application, adding geospatial information. So is there a recommendation on what kind of encoder that could be more effective or give better results than others? I didn't read your paper, so maybe I should just go read the paper.
Yeah, sure.
But if you have a quick answer, that would be great.
Yeah, sure. So actually there is no specific location encoder applicable for every task, or we say perform the best for all the tasks. So maybe for your specific task, you have to try it yourself to try multiple different location encoders, and you see which one is the most suitable for your own task. But they have some rules. For example, we categorize the location encoders into two groups. One is 2D location encoders, and another one is 3D location encoders. So for the 3D encoders, in most cases, they can handle some areas like tropical areas, North Pole, South Pole, better than the 2D encoders, because they think the Earth, our globe is a globe. It's not a plan map. So that is why they can handle those spherical problems.
Excuse me, thank you.
And also, I want to mention that our results of geographic bias indicate that the tile, the most widely used location encoder, actually has the lowest geographic bias than other location encoders. But one thing you may want to consider is that the tile also, in most cases, have the lowest performance compared to other location encoders. So basically, it's a trade-off. You want high overall performance quantified by R square, or quantified by accuracy, or you want more fair and less biased performance. That is a trade-off.
Well, I want to add that yes, like same as Qian mentioned, the first thing is, since we have the location encoder framework, it's relatively easy for you to initialize all the location encoder and test them, like all of them in your model architecture, and to do some ablation study to see which one performs better. And yeah, generally, if your data set coverage is very big, like a world data set, then like Tian said, like spherical location encoders are better because it considers the spherical space. Otherwise, if your study area is very small, it's like in a city or like in certain country, then you can try like 2D location encoder, because in that case, the spherical space does not matter that much. And the third point is, if you're, for example, doing something like about urbanization, then you can check our performance table, like image regression for example, population density or night lights. And if you're doing sustainability related work, you can check our model performance on the system bench, which is more similar to your task. So that's some takeaways as well. Yeah, but that's a good question.
Yeah, wonderful. Thank you. So maybe I have one question related, maybe in terms of you took part in the Spatial AI challenge, and this was the work done through that thing. So we have a new version of the Spatial AI challenge, which is happening soon. I guess the call has just been released a few days ago. So any advice to people who might be here, who might taking part in the next Spatial AI challenge?
Oh, well, I can start with and Qian can add on my oh, I forgot to turn on the video. Yeah. So one thing is I do notice that like in the iGuide platform, if you upload your tutorial, like the Jupyter Notebook tutorial, for example, with a GitHub link, it will use the preview of the GitHub link, like whenever the first time you upload it, like so like after you make some updates, the preview in GitHub won't change. That's what I noticed, and I think I also like talked with you, Annan, about that. Yeah, I guess like I get may like update this function like in the platform later, but if you want your preview look very good like in like a platform, then you must like you better have a better developed tutorial and then put the link to iGuide, because our our first draft is very very simple, and we didn't put in a lot of details, so like the preview in iGuide is not that good.
Okay.
Yeah, that's one thing that we noticed. And but like generally I get platform is like I think it's very useful for replicating or reproducing some results. And I think one suggestion is I learned a lot from the good examples, and also like we can learn from the winners from last year as well. They provide very great framework and graphs for the data sets and models and papers card. Yeah, and yeah, and also like I want to appreciate like you and like people like in iGuide to for providing this kind of opportunity and also this platform for people to share the results, because reproducibility is a main problem in academia, I guess. Yeah.
Thank you for that answer. I know that that is one of the things that we have it in our development things. It needs to be, I guess it's in somewhere in the priority list, I guess. The other thing I would say is like we now have like this. This is like from the time that you took part to it. Now I guess we have ability to upload the data sets itself to be hosted on the iGuide platform, not just somewhere else, and make it available across the thing. And soon we will be having capabilities of issuing a DOI for your data sets, original data sets, and hopefully future notebooks and other things. So so there are lots of things coming along from the iGuide platform side, since Nemin brought that up. So I thought I should mention that. But thank you for that. Any other questions, I guess, for Nemin? Diana, back to you.
Well, thank you very much, Anand, for shepherding those last few questions. It was really interesting to hear how this activity might work even better with the iGuide platform now. And again, everyone, we're eager to let you know about our current Spatial AI challenge. And thank you very much, Qian and Nemin, for sharing this with us today. As I said before, we will process the recording and have this up available on the website. And please pay attention to our VCO page. We've got a lot of new things being added all the time right now. All right. Thanks everyone very much for your time.